All right, day 20, starting now. I see. We have some kind of grid. What are we supposed to do with this grid? I see. Like a cellular automata. Okay. Place. Uh, low and C high. This is in C. Low -5, C high +5. Like that. Uh, enumerate. Ah. Need this. Zero two seven. You're right. Wasn't right. Uh, ten. Oh, 33. Heck. Hmm. That's the high bit. Okay. 7380. Ah, shit. Damn it. What's 7380? 7380. Hold on. Okay. That image looks correct. 405. Good. Maybe you got this? No. Can this bit be on? Insane. $34. What? Can the first bit be on? That's insane. That means that every pixel, it's an infinite image. They can't all be on. Maybe they can all be on? Off. Uh, mhm. Correct. I got a couple points. Yeah. Well, yeah, that wrong submit was actually not good. It cost me 5 minutes. Okay, so what was going on here? This is a weird problem because of that first pixel being on, which I definitely did not expect. Okay, so what's going on here? So we have this grid of numbers, and then we're going to apply this cellular automaton rule, which is like Conway's game of life, if you've heard of that. And so the rule is that to calculate if you're on in the next generation, right? So you can think of this as like evolving in generations, right? So this is the grid on step 0, and then we're going to apply some rule to each pixel of the grid based on its neighbors, figure out what it is on step 1. And you're supposed to imagine that outside of this grid, everything is off, right? There's an infinite sea of dots. And so what is the rule? So the rule is that you look at your 9 neighbors, and then you interpret that as a binary number. So, they give this example, right? These 9 neighbors become this binary number, which if you read it in this direction is 32. So like this is the high bit of the binary number. This is the low bit. And then you're given this rule string, 512 characters. So you look up 32 in the string, I guess 34. And if it's a hash mark, then you're on. And if it's a dot, then you're off. So you're just supposed to apply. So in part 1, apply this twice. How many things are on? In part 2, 50. So the trick here is that, or the tricky thing about this is that if you're surrounded by all off, you're supposed to turn on in the next generation, which is weird because, we said that there's an infinite image where everything was off. So after one step, there's actually an infinite number of things on, right? Everything sufficiently far away from the input image is on, which seems crazy. But on the next step, they're all going to turn off because there's another rule that if you're surrounded by on, then you turn off. So on the odd number generations, like there's an infinite number of pixels on. Can't put that into advent code. But on the even number generations, it's finite, right? So like, this image is evolving, but the whole rest of the grid is flashing from, on to off. From off to on, back to off. So I would say the tricky part of this problem is handling that, infinite sea of on in the odd number generations. Okay, fine. So how do we actually do this? So, first is just reading in the data. So get a rule string, get the initial state of the grid. I decided to represent those pixels that were on as a set. And then the heart of the code is just the step function, right, which takes the grid and returns the next grid. And it also takes the second parameter, which is sort of whether, right, because of this issue I was talking about, where there's an infinite number of on things, obviously we can't have an infinitely sized set in our language. So for those generations, we're going to keep track of what's off instead of what's on. So this is telling us if means G says what pixels are on equals false, means G says what pixels are off. Okay. So I guess a good point is that if you're sufficiently far away from the current pixels of interest, like you're not going to be interesting, right? Like this guy, we know that he's surrounded by off pixels. And so basically we need to, this like interesting region can only go by 1 on every step. So figure out the, basically find a bounding box for a region, right? The smallest and largest row and column. And then iterate through everything in our bounding box, widened a little bit. Yeah, I don't need to widen this much, but it's fine. And then for each of those pixels, just go through all the neighbors, calculate the binary string, and then if that character of the rule string is on, then you're on. So some details here. So we said this 3x3 string, right? So we want the row above us, and then our row, and then the row below us, so -1, 0, 1. And then we want the cell to our left, the cell in our column and the column to our right. So -1, 0, 1 on column. So it's important that this is ordered, right? Because you go row by row, right? Row above you, yeah. And then column by column. And also the first, like the upper left, guide to your upper left is the most significant bit, right? That's the 256 power. And then the guide to your bottom right is the ones place. So we need to make sure that we're, doing that in the right order. And then there's this on issue, right? So we want to know if the cell is on, we add it to the bit. Well, so we know if it's in G, and then whether or not G is on or off depends on this parameter. So this is like, is the cell R plus GR, C plus DC on or not? And then also, our output is supposed to be, if on equals true, we're supposed to output which cells are off, and if on equals false, we're supposed to output which cells are on. So we need to adjust that by this on parameter as well. Is that right? I think I actually reverse. Perhaps somewhat counterintuitively. Yeah, so I guess this is supposed to be like what we calculate for G2. Maybe instead of being counterintuitive, I'll just fix that. So then this should be equals, and this should be not equals. And on the first iteration, on should be true. And let's also print part 1. It's not part 1. Cool. Yeah, so, sort of a standard brute force cellular automaton thing, except for this weird twist of the whole grid turning on at every odd generation. So that was kind of cool. I should have done better. I mangled one of my submissions, and then I got locked out for 5 minutes because I got confused. I did not expect this, like, the whole grid turns on and off, so I should have checked more carefully for that. I even looked at some of the outputs and, saw that, but didn't think too hard enough about it. Okay, so anyway, that was day 20. See you tomorrow.